Welcome back to the classroom. My name is Mr. Wong. Today we'll be covering Module 5 of the HSC Physics Advanced Mechanics Inquiry Question 2, which is on circular motion. And we're going to be focusing on this particular dot point here, analyze the forces acting on an object performing uniform circular motion. Okay, so our lesson intention is just to identify some real-life situations that involve circular motion. Our success criteria is being able to analyze the different forces acting on these objects as it undergoes uniform circular motion. So let us begin. Okay, so these are the three scenarios we're going to look at. We're not going to look at the tension on the string today, but we're more focusing on car on a flat horizontal road and a car on a what we call a banked or angled road. So just before we begin, let's again just quickly explain what centripetal force is. Centripetal force is a net unbalanced force on an object in circular motion. It is the consequence in which the object is pulled towards a center point of its circular path. To obtain circular motion, a real force is necessary to generate this centripetal force. What we mean by that is centripetal force is not a real force. Okay, it's a net resultant force that is caused by other forces cancelling or adding up to each other. So let's write that down. Okay, so it's a net unbalanced force, which means it's from other forces cancelling or adding onto each other. Okay, that's the idea there. Now, if we actually have a look at a couple of these scenarios, if we're looking at a person holding a ball or one of these, don't actually know what the sport is called, hammer throwing. The hammer thrower, when they spin it, it gives that nice circular motion. Now, the reason why there's a circular motion is because of the tension force exerted on by the individual pulling the object in, as the object has a velocity, tangential velocity of going horizontally. We also have satellites. So the contributing centripetal force would be gravitational force. And if you're driving on a roundabout around a particular road, the cause of that is friction of the road pulling the car towards the center point there. So those are just some examples of where the net resultant will come from to cause this centripetal force or to see this circular motion. So let's try and draw some force vector diagrams on these scenarios. So imagine we're a hammer thrower, or we have some kind of mass object on a string here. Let's try and look at what are some potential forces that are acting on it. So assuming for our ball has a particular mass of m, it'll have a gravitational weight force pulling it down. Okay, so gravitational force. We can also see that there must be some kind of force on the string in order to pull it up. All right, so there's that. What we will know is if we break this down into little components. So I'm talking about the tension force here. So if we talk about the y component of our tension force, it goes directly up. Now this force should technically cancel out this force here, the gravitational force, assuming if this object, when it performs its circular motion, it's suspended at a certain height. So it's spinning at the same height, then that would mean that Ft in the y component is equal to Fg in the y component as well. there is another component of tension force, and that is the horizontal component of that tension force. We call that the X component. And if you actually have a look at this diagram, assuming there's no air resistance, because that complicates things, but the assumption we can make here is there is no other force pulling this object in or out, left or right, that is. And so this tension force in the X component is also equal to the net force of this circular motion, which is therefore our centripetal force. So in this scenario here, the horizontal component of our tension force is the net resultant force, is the origins of our centripetal force. Okay, so there's that. What about a satellite in orbit? Now, a lot of people get this idea that if it's a satellite in orbit, it has a force pulling it this way, and then a force pulling it down, like so. So this is fine, the gravitational force pulling it down. But there is absolutely no force in the horizontal direction for our satellite here. Okay, what's actually happening? Remember, we're going through uniform circular motion. The very definition of uniform circular motion says we have a circular path, but the speed is constant. So there is no force if an object is moving at a constant speed. Take that into account. So this is just velocity here. If I was to draw a proper force diagram for my satellite scenario, then it would be just this. Just the force going to the center. Okay, so let's go to our next example. Okay, so we have a gravitron and we have a curved flat road. Now, for those who are in Sydney, Australia or Melbourne, the gravitron, you can actually find it at Luna Park. So it's one of those where the machine spins really quickly and you get stuck onto the wall. Okay, so we need to work out what is the reason or cause for this. Now, on the gravitron, you have your gravitational force. Okay, so there's that. Next question is, if you're on the gravitron, you don't appear to slip up or slip down. Okay, so that indicates that there's something balancing out our gravitational force. So I'll draw an arrow of similar size. Now, the idea is this force would be from friction. Because if you imagine, to stop your motion from falling down, if you're touching a surface, then friction is causing the same amount of force pulling you back up. So what's the thing that prevents you from flying in, or what's the cause of your centripetal motion here? Okay, so what is our centripetal force contributed by? Well, you are stuck onto the surface of an object. Remember, if you make contact with any object, there's also a normal force that is placed onto you. So for a gravitron, the origin of your centripetal force is actually from the normal force of your body touching the surface of the gravitron. Okay, what about a curved flat road? So we're trying to turn a corner around the road. We have our gravitational force down here. We have our normal force up here. And we also have this going through. Now, say, for example, I'm trying to turn. My acceleration is going in this direction. So acceleration is going that direction, and I get at that curved path. So what could be the cause of this circular path? Well, the only thing that's on the road, really, in terms of forces, is friction. So friction is the origin of our centripetal force in this scenario here. You might want to write that down as well. So that's how you do that there. Okay, so that gives us a nice sort of force vector analysis of the different objects undergoing uniform circular motion. So let's now look at some other analyses as well. Okay, let's focus on the car moving around a horizontal curve, or doing a horizontal circular bend. Okay, so we have an object, or we have a car that's moving in this tangential motion here. When it turns, its acceleration is pointing towards the center of its circular path, right? And also has an acceleration. So force, acceleration, we have that as well. Now, just one thing here is that the reason why you experience sort of a pulling sensation towards in the opposite direction of where your circular path is because of your inertia. The original inertia is going this way across, and as your car is going down this way, your body isn't actually being pulled away. It's essentially your car's moving, but your original inertia is still going in the original direction. So that's kind of like Newton's first law of motion. Okay, so when a car is turning, it experiences static friction. So this is the provider of the centripetal force. What do we mean by that? Remember when we said there's two types of frictions. There is kinetic friction and there is static friction. Now the reason why the car turning experiences static friction and not kinetic friction is because the car is moving or opposing a new direction, right? Kinetic friction is caused by your car moving in the same direction. Static friction is trying to create new motion from a motion that wasn't actually there. So by you turning, you're actually trying to overcome static friction instead of kinetic friction. So if the car's speed is increased, then it will need a larger radius curve. So let's do a quick analysis. Now, say for example, our centripetal force is contributed by the static friction it's trying to overcome. Now, what I mean by this bottom bit down here, if we increase the car's overall velocity, let's do this. So centripetal force is mv squared over r. Okay, now assuming that obviously static friction is constant for the road, right? If I increase the velocity of my car moving and our centripetal force is the same, right? We must then travel a larger radius. So what we can see here is if all these values are constants, the velocity of the moving object is directly proportional to the radius of its circular path. So if velocity was to increase, so would the radius of the object's circular motion. We've shown this before in one of those simulations, so you could always check out last lesson to look at that. Okay, so we can simply show it like this. So the net force is, or at least for our scenario here with a car turning on a horizontal corner, is contributed by the friction force, if you recall. That's the friction coefficient times our normal force, which also can equate to mv squared over r. Okay, I'll go through some calculation questions again in a separate video, but let's go on from here. Okay, so the next scenario we're going to look at is circular motion on a bank curve. What we mean by a bank curve is this: circular motion on a slope path or angled motion path. This one will take a little bit more interpretation and force vector diagram, so let's try this. Okay, so compare the pair. You have your flat road turning around a corner, and then you have a kind of angled road turning around a corner. Okay, now you might wonder specifically why would we design roads that are on a curve like this, on an angle, instead of a flat road? And there are a couple of reasons. Sometimes it could be just geography. You can't really build the flat road on really rocky mountains. That could be it. But there also needs to be some consideration to the forces. So let's look at this and try and work out what type of forces are acting on our car here. So we have the gravitational force, as you can see, that moves directly down. We also have the normal force going in this direction. Now you might wonder why the normal force isn't going directly up like this, but remember the definition of the normal force is it acts perpendicular to the surface of contact. So if I actually draw this line a bit further down here, that is directly perpendicular to our surface there. So keep that in mind, okay? All right, next part is then to work out, what type of forces are occurring at this point in time. So if we look at the normal force, there has to be a vertical component and there has to be a horizontal component of our normal force, right? So we have our normal force, if you remember your good old trigonometry. So that can be our angle here. So we have the hypotenuse, we have the opposite side here. So to find the F normal x component, it is F normal times sine theta. Okay, so that's for this bit here. For the Fy component, or F normal y component, that is our normal force times cos theta. Okay, so our net force in this case is contributed by the F normal force times sine theta. Okay, this is with the assumption that there is no friction. What if we did have friction? What would that diagram then look like? Okay, so I'm going to do a different color for the friction force, but friction force is going in this direction, right? So friction, that's given as this times our normal force component there. Now, as you can see, our friction force is also at an angle, right? It's at an angle like that. Now, assuming that we can sort of draw our vectors sort of down here. So this is what we have. If I was to try and find the horizontal component and the vertical component, what would it look like? You can sort of imagine theta is this value here. Okay, so the horizontal component of my friction force, so F friction of the x component is equal to, we have the hypotenuse, we have the side here, so, or the adjacent side, so it would be cos theta, so it would be F friction times cos theta, and it would be the add up of these two forces that would give us the net force, assuming if we have friction. But there aren't many questions out there that will ask you about finding the friction force. So this here, this bit that we have here in the sort of purple, this is additional stuff. So this is additional. If you find this part confusing, you can try one or two past paper questions on it, but don't get too bogged down by that, okay? Okay, so I'm just going to focus back on just assuming there is no friction. What else can we write with this equation? Well, the normal force, if you remember, is caused as a component of our gravitational force. Okay, so that's what we can write out. If we look at what the normal force is, okay, we can actually work that out from our gravitational force. So our gravitational force, this goes back to when we were solving components or at an angle on a bank surface or inclined plane. So using Fg as the example here, for this side, it would be, or this component would be described as Fg, let's see, cos theta. Okay, and what that essentially means, that is the opposite component of our normal force. So if I substitute this formula into here, knowing that the gravitational force is m times g, then our formula kind of looks something like this. So let's show that on the next slide. Okay, so if we have our net force, so we'll just rewrite that. In our scenario of ignoring friction, we can substitute the normal force for the gravitational weight force component. Okay, so this bit added on, you get this formula here, and we can rewrite it as mg tan theta. Knowing that the centripetal force is mv squared over r, we can also equate this equation together. So this is using the component of the gravitational weight force, tan theta, and this will be the centripetal force experienced by an object going through a banked road. This is the formula to describe. But we can actually go a bit further with this formula as well. So we can actually work out a thing called design speed. The speed in which traveling for that vehicle does not experience any sideway friction, meaning by at this point in time, it's a nice uniform circular motion that we are going to get. So equate this equation together. Okay, and we want to make v the subject of the equation. So let's try and show that. Firstly, move r over in the equation, and we can actually see, or actually before we move r over, we can see these two m's will cancel each other out. So we get a formula like this. As you can recall, v squared over r is just centripetal acceleration. So centripetal acceleration on a banked curve can be expressed as g tan theta. But if I want to move r over, I get r squared on g that, and then we get v equals to the square root of r g tan theta. Okay, so this is an expression for design speed, so the speed at which an object can travel without any sideways friction. If we want to find the angle, we can just rewrite the equation like so. Okay, so what's the purpose of using banked curves? Well, banked curves doesn't require sideways friction to generate centripetal force. So the curve itself is going to pull the object down. Obviously, we're assuming that there's no friction on it. So that means vehicles can travel a lot faster around a banked curve, and the vehicle won't skid off path. So that's kind of the reason why we do design particular courses as banked curves. So in those biking arenas, indoor biking arenas, the reason why it's banked, the bikers can actually travel at a much faster speed without worrying about deviating their path or potentially going out of control with the crash, because there's a much stronger net centripetal force pulling them inwards. Okay, and so that's what we know as the design speed, the speed at that the object can go without drifting up or down. So those are the formulas we're going to look at for the bank corner curve. these ones here. Now, these ones you need to take into account because they're not on your formula sheet. Actually, most of the formulas that we looked at today are not part of your formula sheet, so you do need to remember how to derive these there. All right, then that concludes the lesson for today. Thank you so much for joining in. Obviously, there was quite a lot that we had to unpack for today's lesson. So thank you for listening up to this point here. Like I said, the tutorial video for how to perform the calculations will be uploaded as well with this one. So once you've done this, have a go at doing the calculation questions as well. Until next time, take care.